Okay, and time to get started. So last time we were talking about linear approximations, and reminder, we modeled the idea off of this formula that came from this set of criteria. We want anything that we're going to call a linear approximation, it better agree with the function both in value and in derivative at the point in question, right? So in other words, we're doing the linear approximation, at a certain point, linear approximate at a certain point, so A. So it's at that point A that we need for that function, the linear approximation to mimic the function. Okay, so you write down the same criteria for a multivariable function, and you get this formula right here, which structurally actually looks a lot like the original formula. And then when you make up the appropriate notation and rewrite, now it looks even more, honestly, like the original formula. There's f of a, and then some kind of a derivative times x minus a. It's just that now this derivative is a vector of a bunch of partial derivatives. And x minus a is now not just a scalar, now it's a vector. And times is no longer scalar times, it's now the dot product, one of our primary operations on vectors. So nevertheless, adapted to a vector context in some sense, but very similar looking, right? And we saw an example last time. Okay, so then we're skipping again. This stuff on the next few pages is matrix oriented. It's Math219 stuff, and I'm not going to go through this. It's not part of the course here. We'll say something related to that a little bit later. So next thing I want to talk about though is tangent planes. So a lot of students conflate the tangent plane with the linear approximation. Feels like they're kind of the same thing, right? I mean, isn't this that's the tangent line, but isn't that also the linear approximation? Aren't they kind of the same thing? Very important distinction, though, and this relates to something we talked about last week, or maybe early on Monday. I've already forgotten. But that is, you got to make sure to distinguish a graph from the function itself. They are not the same. A function is a fundamental mathematical object. The graph of the function is kind of an arbitrary made-up construction that generates a picture from a function. Again, really not the same thing. Okay, so that's the distinction between linear approximations and tangent lines. The linear approximation is the function that we just talked about that has certain properties, that it's derivatives of blah, blah, blah. The tangent line is the graph. Right? Remember what a graph is. A graph is what you get when you set the values of the function equal to a new variable. Right? So it's the act of setting L equal to a new variable y, that's what creates the tangent line itself. Okay, so that's a rewind, of course, to single variable calculus, but I feel like that has to get said because in single variable calculus they tend to sweep under the rug all this business about graphs. So now let's apply the same idea now in a multivariable context. And again, we have this already established formula for the linear approximation, old news. So what's the difference between that and the tangent plane, you might call it? Well, again, the tangent plane is the graph of the linear approximation. So, sure, if you have a function of two variables, and notice my original function f here is a function of two variables, and you can talk about the graph of that function. Now that we have the graph of that function, which of course you see as a surface, now I can talk about the graph of the linear approximation. We call that a tangent plane because, well, for one thing, it's a plane. And for another thing, it's a plane that's the graph of a function that has a lot in common with f, right? So the purple surface is what you get when you set z equal to f. The blue surface is what you get when you set z equal to L. They're not exactly the same functions, but they mimic, right? They have the same value at the given point, so therefore they touch at that given point. They have all the same partials, so they have all the same slopes. And therefore this blue plane is tangent to that purple surface. So totally analogous to the idea of a tangent line, just sort of one dimension up. And by the way, likewise in higher dimensions, now you'll notice in my picture, I only had two input variables because, well, of course, my hands are tied. I've got to draw a picture. The best I can do is pretend to draw a three-dimensional picture. I can't even pretend if it's four-dimensional, right? So, again, my hands are kind of tied. This is the most general case that I can draw here. But that said, this formula for a linear approximation works in any dimension, right? Just dot product with the gradient, and then the idea that you can look at its graph is also works in any dimension. You just can't draw the picture. Okay. All right. Is everybody happy? All right. Okay. So I'm going to move on now to. By the way, you'll notice I'm kind of bouncing around in my Math219 notes here. That's because I'm going in order in my Math212 notes. And so the next thing to talk about is higher order partials. It's just like in single variable calculus. In single variable calculus, you have a function. You can talk about the derivative of the function. And that derivative is itself also a function. So you can talk about its derivative. And you can go as many times as you want. So likewise, if you have a function of several variables, something that you could take a partial derivative of, well, then the partial with respect to one of those is also a function of several variables. And so being as it is a function of those same several variables, you can talk about its partials too. So let's see that in action. Here is a function of x and y. I can talk about the x partial. I can talk about the y partial. Easy to compute. We talked about these notations. All of this is old news. But now, observe. In the same way that f, you can see right here, is a function of x and y. Well, so is this partial with respect to x also a function of x and y. So I can talk about its x partial, its y partial, which I had to kind of bend this arrow here because I ran out of space. Paper isn't wide enough, unfortunately. But we can talk about its partials just as well as you can talk about f's partials. Okay, so now let's talk about notation a little bit. The actual computation of the partial derivative, of course, is easy. The y partial of that is clearly that formula right there, nothing to it. But let's talk about notations. Okay, so we have pre-existing this notation here, f sub x, as a notation for the x partial. There it is, f sub x. Now the act then of taking the x partial of that, if I again use a subscript to indicate the act of taking the x partial, notice that gives me overall this notation for a second partial with respect to x. All right, now on the other hand, we also already have a more Leibniz-like notation. Now let me switch to the other partial just for sort of convenience here. We have this notation for the x partial, and I can represent the action of taking the y partial by, again, Leibniz notation, taking the y partial there of that x partial. And notice that gives me sort of, that's the motivation anyway for this notation. And I, by the way, I've always been a little uncomfortable with this notation. There's a bit of an abuse of notation here. I just want to point this out just so you're not as weirded out as I used to be. But you see two partials next to each other, and so they write that squared. It's not squared. We're not multiplying partial times partial. It's not what that is. It's just notation acknowledging the fact that there's two partial symbols right next to each other. So please forgive the sloppiness on that. It's just notation. Okay. All right. So those are the notations. There is something a little confusing and awkward about this. If you look at, again, that, we have these notations for the x partial, and I can take the y partial, Leibniz notation like that, Newton notation, Newton-ish notation like that, and notice it kind of on the other side, right? The Leibniz notation's on the left, the Newton notation's on the right. So that results in there being a kind of an inconsistency in how you denote the order of the partials in these new notations as well. I wanted that a different color. So is the y on the left or is the y on the right? Does the first one on the left or the first one on the right? Well, it depends on which notation you're using. And again, my apologies. I was not involved in the decisions about this notation. It's very unfortunate. But it's reality. These notations are both out there. They're not going anywhere. So heads up, be on the lookout. Every time you see these kinds of notations, you have to take an active role in interpreting. Wait a minute. What kind of notation is this? What does that mean? And therefore, which one of these partials happened first? Is that cool? Everybody happy? Yeah. That's annoying. Okay. Now, one thing you might notice, and I computed a bunch of these partials here, well, a couple of them anyway. And what are the odds? Check it out. Weirdly, these are the same in this case. How about that? That's strange. Is this a coincidence? No, it's actually not a coincidence. And it turns out that this is true, I'm going to say, pretty often. I don't want to quantify that because, we tend to look at very nice functions like, differentiable, continuously differentiable, infinitely differentiable, smooth functions. We look at nice functions most of the time. And in the nicer the category, the more of these happy coincidences happen. And again, they're not really coincidences. So in general, most of the time, it's going to be equal no matter how you rearrange the partials. But there is a condition. Again, most of the time, this condition is going to be satisfied. The condition is that the function in question, whose partials you're talking about, that function has to be what we call CK. And what that means is CK means that not only is the function continuous, but the partials are continuous. The second partials are continuous. The third partials, the fourth partials, blah, 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 all the way up to and including the kth order partials. Thus the K in the notation. Right? So, in other words, it's got to be a pretty nice function. But if that's the case, if the function is CK, then up to and including partials of order K. Rearrangements don't affect the result. Okay. All right. Is everybody okay? By the way, in practice, here's how we tend to use this. We don't actually, most of the time, actually manually check all of the kth order partials. Oh my gosh, that's a lot of partial derivatives to compute. In practice, we tend to make certain observations, such as, for example, take any polynomial. All of its partials, we know already, are also polynomials. That means that all of the higher order partials are all polynomials, and all polynomials exist, and all polynomials are continuous. Right? So that's in practice how we tend to use this result. Okay. So likewise, for example, all functions that you can get by multiplying polynomials times exponentials. Yeah, same. You can make a very analogous argument. Okay. So what do these look like? Let's take second order partials in particular. What do second order partials look like? Now think back to single variable calculus, and you saw in your Calc 1 classes that second derivatives kind of tell you about the concavity of the graph, right, geometrically. Good news. Very similar result here for multivariable functions of two variables anyway. I'm going to draw here the graph of a function of only two variables Because again, I run out of dimensions otherwise, and I need to be able to draw pictures. So that's why we're looking only at two variables. But anyway, here's an example, and let's think through now how would I understand fxx. What on this picture tells me about fxx? Well, I'm taking the partial with respect to x, which means I'm holding y constant. And if y is being held constant, then we're looking at a cross-section in a plane perpendicular to the y-axis because y is not allowed to change. And in so doing, we'll then notice that the act of taking the x partial and then taking the x partial of that, I'm really just taking the second derivative of this single variable function whose graph is the cross-section, just like we discussed when we were talking about partial derivatives last time. So, I mean, it's morally a single variable function because y is held constant for both of the x partials. And so, just like before, the second derivative is just the concavity. And you can see as I have this picture drawn here, that cross-section perpendicular to the y-axis, parallel to the x-axis. Think about it whichever way you prefer, right? But that's concave down, and so I would interpret here that fxx must be negative. Is that cool? Everybody happy? All right. Likewise for fyy, and just real quick, I'll point out that if you're taking fyy, that means that x is constant. That means that I'm stuck on this cross-section, where the cross-section looks like that, and I'm effectively treating this now as a single variable function of only y, in which case the second derivative tells me about, again, concavity. This time concavity in the other direction, though. Right? And so here, concave up in the y direction would mean that fyy is positive. Everybody good? Okay. Cool. All right, now, here's where it gets weird. Both of these were second partials, but with respect to the same variable for each partial. That made it easy. That made it truly a single variable function that I was looking at throughout the whole story of the calculation, and effectively it reproduces single variable results. Here's something it doesn't. What if I'm looking at a mixed partial? This is weird. This is a very weird situation because for the purpose of the very first partial I'm taking, y is a variable. Because I'm taking a partial with respect to y. But then for the second half of the calculation, y is no longer a variable because for the second half of the calculation, x is the variable and y is now a constant. So y is a variable sometimes, it's a constant other times, and likewise x is a constant at first and then it becomes a variable. This is not Calc 1 all over again. Does everybody see why this is a much harder problem? All right. So now there's a point of view that I think is particularly nice on this. I'm going to interpret these in a very carefully chosen way. I'm going to interpret my y partial as representing slopes of tangent lines in the y direction. I'm then going to interpret the x partial differently. I'm not going to interpret the x partial in terms of slopes. I don't have to. I've got other interpretations. And in particular, I'm going to interpret the x partial as representing how fast things are changing as I'm moving in the x direction, which is one of the other interpretations we talked about. Okay, so here we go. And I'm going to have to zoom out to fit all this on the screen here. I struggled, by the way, in deciding how to draw this picture. Initially, I was trying to draw an actual surface that kind of did something kind of like this, and frankly, it ends up just messing up the picture and creating more confusion. So I'm not going to draw the surface itself. The picture just gets weird. What I'm going to draw is the appropriate tangent lines to the surface representing the derivatives in question. So let's start with the y partials and take, for example, at this point in the domain, then this, we're up here somewhere is where we are on the graph. And as I move in the y direction, right, there's the y direction, I want to know what the slope of the tangent line is in that direction. So the tangent line in that direction is going to be some line, I don't know, it depends on the surface I didn't draw. But there will be a tangent line. Let's say, for example, it might look like this. Notice that is what you might call in the y direction, because it comes from looking at how the function is changing in the y direction. Is that okay? Is everybody on board? Okay. Alrighty. So that said, what do I do with this x partial of the y partial? I'm going to need to understand how those slopes are changing as I move in the x direction. So I'm going to look at, for example, what is the slope of the tangent line in the y direction there, and then I'm going to start moving in the x direction and see how those y slopes change as I move in the x direction. And so you see here, and each one of these tangent lines that I have here is in the y direction, but I get from the one to the other by moving in the x direction. Does everybody see what I'm trying to draw? It's a tough picture. So, okay, what's happened here? What are we seeing? What would you say is this x rate of change of the y slopes? And just looking at the picture, I appeal to your geometric intuition. Here the y slope was heavy negative. Here it was somewhat negative. Here it was slightly negative. Here it's about 0. Here it's positive. I don't know about you, but it seems to me that as I move in the x direction, those y slopes are increasing. So this, in this picture, as I have it drawn, would be positive. Cool. So now there's different versions of this. I mean, I drew a bunch of arbitrary slopes there and arbitrarily had them changing as I moved in the x direction. It's not always going to be exactly like that, of course, right? But the pitch that I'm trying to make here is that this is kind of the thing that you're measuring when you're taking this mixed second partial. So looking again at this picture, I'm going to propose that you could interpret this as representing a kind of a twisting of the graph. And again, geometric appeal, right? And I don't have a model of this kind of thing, but imagine that I had a sheet of rubber, about, let's say, this big. Imagine I'm grabbing it by the four corners here, right? And doesn't it look like I'm kind of twisting it sort of like this, right? It's kind of sort of, again, hard to visualize. But anyway, that twisting is what causes those y slopes to increase as I move in the x direction. So that twisting is what this mixed second partial is measuring. Mixed second partials measure a kind of a twisting of the graph. Okay. Alrighty. Let's see here. Okay, right. I need to come back over to here. So, before going to the next thing, this is back in my Math212 notes, by the way, you'll notice, page 69 of the Math212 notes. So, this is just a FYI, just, to let you know why we care about these kinds of things. There are a lot of important physical equations, physical concepts, tools that we use to understand the physical world that involve partial derivatives. Partial derivatives are extremely useful in representing these objects. So, for example, if you want to understand how voltage works, right? If you have charged particles arranged in a certain way or whatever, maybe there's just a single charged particle, and you want to know how to compute electric potential given some arrangement of charged particles. And in general, that's a very hard problem. But the solution is going to have to satisfy this equation. Now, why this equation? That's a long conversation. That's not what we're here for. That's a physics thing. But notice the result. The way we understand potential is with an equation that's all about partial derivatives, right? That's the point I'm trying to make here. Partial derivatives are an essential tool in understanding voltage in the vicinity of electric charges. Partial derivatives are an essential tool in understanding how heat moves. That's a pretty big deal, right? Partial derivatives are a critical tool in understanding how waves move. Again, a really fundamental physical concept, right? And it's all about partial derivatives. And by the way, just FYI, this right here is another notation. It is a shorthand for this expression called the Laplacian. It's called the Laplacian because it shows up in Laplace's equation. Okay. Oh, and by the way, do be careful. The Laplacian is indicated by what really actually kind of does look like a capital Greek letter delta. But it's what I'm going to call a right side up triangle. Whereas don't conflate that with the gradient. The gradient, where is my, did I, no, it's got to be in here somewhere. The gradient, where did I put it? Well, I guess I don't have that. Anyway, I'll just write it again. The gradient, by contrast, is written as what you might call an upside down triangle. Okay. So yeah, but very important to keep those straight. If you replace one with the other, you end up with a really different statement. So careful, please. Okay, how are we doing? Is everybody happy? Oh, and then another one, Schrodinger's equation. If you want to understand quantum mechanics and how, particles and the nature of matter at the small scale is really weird. They probably told y'all the same little fibs that they told me when I was in high school. They told me that electrons were teeny tiny little particles, kind of like baseballs, and that they go around in circles. That was a fib, and they knew it when they said it. But they tell you that story because the truth of the matter is something you're really not prepared for when you're in high school, right? Nobody in high school reasonably could be expected to understand that, particles are really complex valued wave functions. And it's not appropriate. So they'd make up a little story. Anyway, the actual nature of matter is to a large degree understood by this equation. So again, partial derivatives everywhere. Okay, so moving along. A little bit of terminology. These two words, increment and differential, closely related but importantly different. Increment means the actual amount that the function changes as you change the input. Increment means an actual change in the function. Differential means our linear estimate of that change, or said differently, how much does our linear approximation change? Right? So that's the idea. Now let me draw a hopefully familiar picture when you are doing single variable calculus and you have some function, let's say like that. Oh, that's a baddie. Let me draw a different. Yeah, I can get by with that. Then at a point like, let's say here, for example, you can talk about the tangent line, right? And then if you say, all right, well, from that point, if I move over by some amount, right, and you can talk about the rise and the run and all that, then in this picture, the differential is this side of the triangle here. The differential, again, is a change in our linear estimate. The increment is not, color choices, hang on. Let's see. The increment is the actual change in the value of the function. Not the linear estimate to the change in the function. Does everybody see the difference? Okay. It's just terminology, but anyway, it's stuff that's got to get said. So, okay, that established, recall that we have this formula for the linear approximation. And I mean, a pretty easy little adjustment is to take the value of the function and move it over to the other side of the equation. That gives me L of x minus f of a In other words, L of x minus L of a. In other words, the differential. Right? So I can effectively think of this as kind of just turning into df, our differential on the left-hand side. It's a change in the linear approximation. Okay. On the other hand, now notice, and I'll say recall that we talked previously about how you can interpret those extra terms as being basically a dot product. Just a handy-dandy little notation there. And now let's think about what I have over here on the right-hand side. This x minus a vector is, well, that's the change in the input to the function. I was at the point A. I've moved over now to the point x. It's in the process of moving from A to X that I want to ask these questions about F. And, how much did F change? What's the linear estimate? Blah, blah, blah. So that also we're going to denote as a differential because that's the change in the input. So with all of that noted, this original formula for our linear approximation, I can rewrite the whole thing and I get this, that the output differential and the input differential are related by way of dot product with the gradient. So now I'm going to call you back now to one of the very first things that we said about derivatives. Remember I said there's a bunch of different kinds of derivatives that take different forms, that are interpreted in different ways in different kinds of pictures. Oh my gosh, right? But the unifying feature that all derivatives have in common is that they relate input changes to output changes. Well, that's what the gradient is doing here. The gradient here is pretty literally something that allows you to take an input change and turn it into an output change. So we really should think of the gradient not just as a kind of a notational shorthand, because I don't like writing dot, dot, dot all the time, right? I presented it as just an algebraic convenience, just a notational shorthand. But no, we see now the gradient really is fundamentally it is the derivative. It's the thing that relates input changes to output changes. That's what a derivative is supposed to be. We really ought to call this the derivative of this function. Is everybody with me? Nice fact. Deep observation, really. It's weird because in single variable calculus, we were accustomed to derivatives being numbers. Weirdly here, for this kind of a multivariable function, the derivative is not a number. The derivative is a vector. So, anyway, that's, like I say, kind of a deep moment there. Okay. All right, so let's see this in action. Now, this is just kind of a numerical example. How do we estimate the value of this function? I think y'all have seen questions like this, a single variable version of these kinds of questions back in Calc 1 classes. If you want to estimate some weird expression, recognize that expression as being the value of a function for certain values of the inputs. Now, here, I'm going to say that what we're trying to estimate is a value of this function, but specifically, it's a value of that function where two things. It's where x is equal to 3. I got this. Oh, gosh. It's where x is equal to 3.02 and where y is equal to 0.01. So, another way to say that is that what I'm trying to compute here, this thing I'm trying to compute or estimate, is a value of this function at a point that's near here but this far away from it. Right? So anyway, there's, again, very similar to how analogous single variable calculus problems are solved. And so we're going to make the observation that, okay, well, look, at this point, it's really easy to evaluate this function. How much does the function change if I change the input by this amount? Well, we have our relationship here between input changes and output changes that I'm trying to compute. Dot product with the gradient allows me to relate input changes to output changes. Approximations, of course. And so now it's just kind of a matter of plug and chug. I've got to take this function, compute its various partials. Right? That's what a gradient is. Gradient is where you take the various partials and assemble them as a vector. Then I dot product with dx. That gradient now, of course, that gradient, I have to evaluate that at the point where I'm doing the linear approximation. So at the point where x is 3 and y is 0, because that's the handy-dandy convenient point where everything's easy to compute at 3, 0. Right? And all together then, it turns out that the gradient at the point in question is this. We dot that with our dx vector and a little bit of arithmetic, not much to it. And let's see, all together, our differential given by this dot product is approximately, I should include the approximately here. It's approximately that value. Is everybody good? Now, it's easy to spike the football here on the 2-yard line, but we do have to actually, don't forget the critical detail. All we've computed is our differential. We've computed our estimate of how much the function has changed. We have not computed an estimate of the value of the function yet. It's just that we think it's changed about this amount between where we started and where we wanted to end up. So I do have to actually take the actual value of the function. Now this is a little bit of arithmetic, but if you take the original point, a, and plug that into this function and compute, you do end up with 2. Right? And so the actual estimate, or linear estimate to the value of the function, is what you get when you add the original easy computed value with our differential estimate of the change. And altogether then, our estimate is that it's approximately this. And now just for the comparison purposes, you could plug this into a calculator and find that the actual value is more like this. And notice, this is a pretty good approximation, right? We got valid digits, you might say, all the way down, and we don't really fail until the 5th digit to the right of the decimal. That's pretty good. Okay. Everybody all right? Okay, now, awkward conversation. I'm going to spend hopefully just a couple of minutes here, if I can restrain myself from going on and on and on. But there's a huge amount of stuff to be said about differentiability of multivariable functions, and we don't have time in Math 212. And by the way, we don't have time in Math 219 either. This is really more of a Math 222 kind of thing. But in single variable calculus, differentiability is a pretty easy topic. A function is differentiable if you can differentiate. It's really easy, right? Differentiable is just lingo. Okay, not so with multivariable functions. Very surprising, as it turns out. Weirdly surprising. But roughly speaking, the point here is that multivariable functions, they're functions on a whole, at least 2-dimensional space. There's more different ways that the function can be weird as it moves in different directions. And some remarkably strange things can happen as a result of this. There is I could spend a week talking about all of the ideas that are connected to, related to differentiability, but not quite the same, right? And then eventually talking about differentiability itself. So what I'm going to leave you with is that differentiability is a very subtle concept, and we're not going to be particularly precise about it in this class. In practice, and this is the really good news, there's a much easier concept to talk about, and that is continuous differentiability. Really easy to write down. I'll come back and talk through those details in a moment. Really easy to talk about continuous differentiability, and the good news is that every continuously differentiable function is also this elusive, subtle, deep concept called differentiable. So this is the main thing that y'all need to know about differentiability, is that check to see if the function's continuously differentiable, and if it is, then you can conclude that it's actually differentiable. Now a couple of details. So what is continuously differentiable? What does that word mean? Again, really good news. Really easy to check. You have to compute the partials, or correction, you have to at least identify in some sense what your partials are. You have to confirm that they're defined at the point you're interested in, or over the domain that you're interested in, whatever. Make sure nothing explodes. Make sure you're not taking a divide by zero kind of a deal, or log of zero, or arctan of a place where you can't define arctan, right? Just make sure nothing blows up. And then you need to know that the function's also, the partial derivative, is also continuous. And now again, that's a harder concept, and making that precise is something that we kind of glossed over. That was section 13.3, and we're not going to talk about that. But the good news is that most functions are continuous, and I think you have an idea that discontinuities happen again, where you've got a zero in your denominator, or something fails to be defined somewhere, something conspicuously bad happens. So in most cases, it's conveniently true by casual observation that the function is continuously differentiable, and therefore it's also differentiable. Okay. Is everybody willing to buy that? Now, just real quick, I'm not going to be precise about this, but what does differentiability actually mean? Again, that's a week-long conversation to really treat it, the way I'd like to. And we don't have that kind of time, so I'm not going to do that. But roughly speaking, differentiable it says that these linear approximations that we make, these DF output differentials that we compute with the dot product with the gradient, the formula we had, a couple pages back, that those approximations are good approximations in a very reasonable sense. Now again, what exactly do I mean by reasonable? Week-long conversation, so we're not going to go into that. But morally, what you need to know about differentiability is, it just means your linear approximations are actually decent. That's it. So here's how you write it down formally. Again, you're not responsible for this. It is, again, a week-long conversation. There's a lot to say about this, and we just don't have the time to do that. But I wanted you to know that there is a formal definition of differentiability, and this is what it looks like, and it's pretty hard to work with. And so, thankfully, we don't work with this hardly ever, because I don't need that formula to conclude differentiability. I can use continuous differentiability to conclude differentiability, and that's much easier. Okay. All right. Okay, so off to the chain rule. So, the chain rule is, y'all remember that there was a single variable chain rule. It's how you take derivatives of compositions of functions. It's basically what we're going to be doing here. Here is a scenario. Y'all will recall that if you have a multivariable function, again, here's how you can write the differential. Now, there's different notations you can use, but morally, this is basically the formula for the linear approximation. It's just, written, kind of expanded out. But you can see right in here, you can see the gradient being dotted with the dx, the input differential. So, okay, now and again, I'm going to commit some little math crimes here because I want to get to believable results as believably efficiently as possible, and I'm sweeping a lot of rigor under the rug. That's what Math212 is. If you were to take these relationships between x and y and z, and now presume that all of them are functions of another variable t. So that's what you might call precomposing, right? Assume that everything in sight is a function of t. Then how about this? Just divide by dt, if you will. Right? So I'm literally, missed one. Divide by dt. I'm taking pretty literally the existing formula that we already had written down up here. Just divide both terms by dt and look at what you get. You get a statement. Clear this out. You get a statement here that relates these derivatives and these these derivatives to the composition where I've used z as a function of t. So isn't that nice? I have a chain rule. If I want to take the derivative of a composition and rewrite it in terms of the individual derivatives of the sort of the elemental functions, then boom, there it is. There's my chain rule. Basically just a rewrite of our linear approximation formula. Is everybody okay with that? Okay. All right. And this generalizes to if you have more variables here. I was assuming I had a function of just two variables. If you have several variables, it's morally equivalent. You just get more terms. Okay. All right. So now there's a point of view on how to think about this, and here's where I'm going to switch over now to my Math219 notes. Here's that same formula. I've just, got different names for the variables. But that same formula, I'm going to propose that we can interpret it as follows. Notice I'm interested in computing the partial derivative of one of these output variables with respect to one of these input variables. Right? You can see I have a composition. The z variables are functions of the y's. The y variables are functions of the x's. Right? And all together, I'm interested in a composition, one of the output variables, and how its changes relate to the changes of one of the input variables. Okay. How am I going to interpret this formula? I propose as follows. Let's look at this first term. This first term, the inside of here, partial of y1 with respect to xj. I'm going to draw this arrow right there. Partial of y1 with respect to xj says, look, I'm going to jiggle xj a little bit. As I move xj, that's going to cause y1 to change. And that partial derivative is the factor keeping track of how much the xj change gets magnified to become the y1 change. But now, what's going on with this term, partial of zi with respect to y1? Well, I'm going to draw that arrow. Because that says, okay, yeah, fine, xj changed, that caused y1 to change, but let's be honest, if y1 changes, among many other things that happens, that change in y1 will also propagate along and cause a change in zi. So one of the pieces, right, if I'm interested in computing altogether, as xj changes, how much does zi change? The propagation of the input change along this path, oh, whoops, I used the wrong color there. The propagation along this path contributes that term right there. This is a really nice point of view. It's almost a kind of a geometric point of view on this algebraic equation. You can think of terms in the chain. Let me get rid of all these colors. It's getting confusing. You can think of terms in the chain rule as corresponding to paths from where your input variable is to where your output variable is, paths along which those changes can propagate. And every term, let's see here, every term corresponds to a path, all the way down to and including the last term is this last path. Everybody on board? So it's really nice, really convenient. So when you're trying to write down your chain rule, and by the way, I set this up and so that the z's were functions of the y's and the y's were functions of the x's, and that's convenient. It's arbitrary, but it's at least it's an organized and convenient way to keep track of which variables are where. But in reality, most of the time, when you're using the chain rule, they're not going to be these variable names. There's going to be p's and q's and k's and l's and alphas and omegas and oh my gosh, lots of different things. Right? So it's very nice. Don't try to memorize character for character, and then sort of replace the variable names as needed through, anytime you see an example. That's way too involved, way too hard. Much easier to just say, look, draw your function. Here's one of my functions, input variables, output variables. Here's another one of my functions, input, output variables drawn as well. Notice that the overlap, as it should be if you're composing functions, the outs from the left function are the ins to the second function. That better be the case. Right? And once that's drawn, okay, well, first path, first term. Second path, second term. Et cetera, et cetera, et cetera, et cetera. Last path, last term. So you can generate your own chain rule every time as needed by understanding the relationship between the eventual formula and this idea of propagation of changes along paths. Okay, and then now real quick observation. Notice furthermore that each one of the paths goes by way of one of these, what we call intermediate variables. One of the variables that's in the middle. The output from the first elemental function, the input into the second function. These intermediate variables here, each intermediate variable corresponds to a path and therefore corresponds to a term. For example, we would call this the y1 term because this term corresponds to the path that goes by way of y1. Is that cool? All right, let's see an example. So suppose we are given this question right here. Oh, I missed. Let me try that again. We are given this question right here. F is given as a function of various variables. G is given as a function of various variables. And then I want to compute a certain partial. Okay. So the very first thing I got to do, this is... it's hard to overemphasize how important this is. Draw your diagram representing the composition of these functions. The diagram is what lets you see where are the intermediate variables. What are the intermediate variables? What are these various paths? And therefore, how do you write down the chain rule? It starts with the diagram. Right? So I cannot emphasize that too much. Now I've been asked to compute the partial of z2 with respect to x2. I'm getting ahead of myself, aren't I? Diagram first. F has three inputs, x1, x2, x3, two outputs, y1, y2. There it is on my diagram. Now G says right here, takes y1 and y2 as inputs. Oh, hey, whoa, slow down. The things that came out, I shouldn't use blue for that. The variables that come out of the f function, those are the variables that go in to the g function. Those are the intermediate variables. Those are, that's how the Legos fit together. Right? So that means that G comes after F, and in particular, again, Y1 and Y2 are the inputs, and then now Z1, Z2, and Z3 are the outputs. So as everybody see now, I've taken my functions were given to me in kind of an algebraic way, and I have rewritten it as a diagram. Okay. Having generated that diagram, All right, now we just, you want to know the partial of Z2. Fine, there's Z2. You want the partial with respect to X2. All right, well, there's X2. And how am I going to compute this partial? Well, I just got to take it sort of term by term, path by path. And I can see here there is a Y1 term in that path. Boom, there it is. There is a Y2 path. Bam, there's my Y2 term. And so just from the diagram, I've generated the appropriate chain rule for computing this composed partial derivative. What do you think? Everybody happy? All right, and then some tedium begins. I mean, you do have to eventually, it's annoying, but I got to compute the partial of Z2 with respect to Y1. Okay, well, Z2, there it is, Z2, it says right here, the formula for Z2 is Y1 cubed. I need to take the partial of that with respect to Y1. What is the partial of Y1 cubed with respect to Y1? Well, it's 3y squared. 3y1 squared, I should say. So, yeah, annoying, but you got to do it. Cool? Okay. All right. Okay. Confusion of variables. It is a nasty little landmine problem. So I'm going to start off with an obviously wrong calculation, and then I'm going to fix it. Anyway, here we go. Here's an obviously wrong calculation. There's a perfectly good function, not a thing wrong with it. Here is a perfectly good function, not a thing wrong with it. I've got two perfectly good functions. When you have two perfectly good functions, you can totally reasonably talk about composing them. There's nothing weird about that. Compose functions, fine. I can reasonably ask then that once I've composed them, I want to compute the derivative of this composition. Nothing wrong with any of this. This is all fine. But the question has been written in such a way that you're pretty naturally going to step on a landmine here. Now, deliberately sloppy, deliberately wrong. I'm going to state the single variable chain rule is the derivative of compositions, the product of the individual derivatives. You can write that in different ways. There's the Leibniz form of this, if you prefer, whatever. And I could then sloppily, casually say, here's G, so G prime is the derivative of x cubed, that's 3x squared. And here's F, so F prime, the derivative of x squared is 2x. Now, I'm just playing fast and loose here, but then wouldn't that mean that the derivative of the composition, wouldn't that be 6x cubed? No, of course not. That's clearly wrong. Just directly see that it's wrong because this composition, if I take x squared and plug it into x cubed, I'm going to get x to the sixth, and this is clearly not what it's supposed to be. All right, so where's the mistake? Well, I shouldn't have written down too fast and loose the single variable chain rule. Very important component of the single variable chain rule is that things be evaluated at the right place. So f prime gets evaluated at x. Awkwardly and weirdly, g prime gets evaluated at f of x, not at x itself. That's a certain point of view on what I did wrong. Right? Does everybody remember this little detail? It's always kind of struck me as, I don't know, the first time I saw it anyway, seemed very weird. That G prime is evaluated at F. And if you do that, and remembering that F is x squared, then that gives you an x squared right there instead of just the x. And x squared in that spot makes all of this turn out to be 6x to the fifth, as it should be. So that's one point of view on the fix. But I think there's a much better way to do this. I think this formula here is really very unnecessarily weird. There's no need for this, I think, confusing idea that G prime is evaluated at f of x. It's why? It's not clear. Look how much easier it becomes if you just don't confuse your variables. Here's what I mean by confusion of variables. Initially, G, here we go. F was written as a function of x, so x goes in and out comes some value. G also initially was given as a function of x. It was initially given to where that was x. That goes in to G. We'll check it out. That means that x is in two different places. X is the output from F, because it's got to be the input to G. But it's also the input to F because, well, that's how F was written. So, bad, right? Confusion of variables. I say just basically don't ever do that. Now, there was nothing wrong with the statement of the question. There's nothing wrong with these functions. Perfectly fine to write functions with respect to whatever dummy variables you want. It is also perfectly reasonable for the question asker to then want to say, hey, let's compose those functions. It's your job, right, as the student in this context and outside of this course as the person conducting the calculation, right, to realize that when you compose functions, if you want to have unconfused variables, unambiguous and distinct names for what you might call the input and the intermediate and the eventual output, they need to all have different names because they're all playing different roles. And as such, I mean, you kind of can't avoid this. It says here that apparently G needs to be written in terms of the dummy variable y, not in terms of the dummy variable x. That make sense to everybody? So it's no big deal. Now notice I didn't do anything here. I just took my original function and I wrote it in terms of a different dummy variable. These are the exact same function. G is the same. G didn't change at all. Whatever you give to G, it cubes it. It's just that previously I was calling that whatever you give to G, I was previously calling it X, now I'm calling it Y. Whatever, G is still cubing stuff, right? So this does not change the function, this just removes a really unfortunate choice. So now that said, now let's be fast and loose with the chain rule again. Now here's my irresponsibly, quick and dirty, easy point of view on the chain rule, derivative of compositions, product of the derivatives. It looks like I'm going to step on a landmine here, but let's see here. The derivative of x squared is 2x, no problem. The derivative of, well, it says g of y is y cubed. The derivative of that is 3y squared, which I guess I could rewrite like so. And now notice, I don't have a wrong answer yet. I just have one more thing to be computed. There's that y standing there. That y is the input variable to G, which means it's the output from F, which means it's x squared. And if you plug that in, then just as we should, we get the right answer. 6x to the 5th. Is everybody on board? Okay, so the moral here, don't confuse your variables. Oh my gosh, why would you do that? I mean, it's so much easier if you don't confuse your variables because you just don't even have to keep track of fancy formulas about, oh my gosh, don't forget to plug this into that. No, whatever. Just, you can be as sloppy as you want and you won't get wrong answers if you just don't confuse your variables. Okay, all right. So, all of that said, let me show you the multivariable version of this. Really not that different. So, two perfectly good multivariable functions. Very reasonable question of, I want to take the derivative, I want to take the composition of these functions. So, all you've got to do is then just recognize that if you write, as we have here, that f is a function of x and y. Okay, well, the outputs then these things here, I'd better not call them X and Y. I'd better call them by some other names. Maybe I'll call them U and V. Right? I mean, is that cool? And well, once I've decided to call them U and V, well, that means that when I write G as a function, well, I'd better not write it in terms of X and Y. Oh my God, confusion of variables. I'd better just rewrite it in terms of U and V. Nothing happened. It's the exact same function G, just using different dummy variables to avoid an obvious, ridiculous circumstance confusing my variables. Is that cool? Okay. Okay, now the rest of this example involves the matrix form of the chain rule, which I haven't told you about yet. And so what I'm going to do now is go back, as is done in my Math212 notes, and here's where we were. This is where I picked up in these notes, and we wrote down this equation. And I want to point out that this equation, which we have thought of previously as being about paths and intermediate variables and stuff, happens to be exactly matrix multiplication, as it turns out. Here's how it turns out to be matrix multiplication. So here's the formula, exact same formula. And I'm going to assemble derivative matrices in a particular way. I'm going to let each input variable correspond to a column, and I'm going to let each output variable correspond to a row. And if you organize the matrices that way, then any given element of the product of the two original matrices is exactly as it should be the matrix product, which is of course if you haven't seen matrix multiplication, I'll elaborate on that in just a second. But it's the dot product of this green row of the left matrix with this blue column of the right matrix. And again, now this is the formula that we've already seen. This is the formula that comes from the intermediate variables, paths, propagation of changes point of view, and it shows up in this form if you write these things in terms of matrices. Now, let me just make sure everybody knows about matrix multiplication. This is one of the first things you learn in a linear algebra class. You may have seen this in a high school math class, maybe not. If you didn't, don't worry about it. But matrix multiplication, if you have a matrix here and a matrix here full of various elements, et cetera, et cetera. Oh, my computer is mad at me here. It'll be fine. I hope it'll be fine. If you have various elements in various matrices and you want to compute the product, okay, yeah, I got it. Sorry. You want to compute the product matrix. It's kind of an arbitrary rule, but it comes from very naturally from a good place, but that's a whole linear algebra conversation we can't have. Any element of the product matrix, that element is in a certain row of the product matrix. You're going to look at the corresponding row of the left matrix. I'm going to call it an arbitrary rule. That element that you're trying to compute is also in a certain column of the product matrix. That corresponds to a certain column. Oh yeah, battery low. Thank you. Sorry. Certain column of the right matrix, and the rule for how to compute. Oh my gosh, the rule for how to compute this entry is literally to take the dot product of that row with that column. So notice that corresponds perfectly with exactly what we needed it to be so that this would work out. So it's a nice point of view. You can think of the chain rule on the one hand you can think of the chain rule as a statement about paths and intermediate variables. On the other hand, you can think of the chain rule as a statement about all of these partials of the composition relating to all of these partials of the one function and all of these partials with the other function. And they all just, the pieces fit together. It's a perfect little dovetail circumstance. The matrix multiplication structure does all the bookkeeping for you. It keeps track of which you multiply by what. In some circumstances, that's really convenient. Okay, how are we doing? Everybody on board? All right, oh, my battery's low. Okay, let's see here. Where were we? Yeah, right. Okay, so that's what happened with the rest of this question. I wrote down the matrices showing all the derivatives of, colors. All the derivatives assembled as a matrix for the one function, and then all of the partials of the other function, again assembled as a matrix, and you compute the derivative of the composition, the derivative matrix, that is, of the composition as the product of those individual derivative matrices, and you got to multiply that by that. And then notice, some multiplying stuff out ensues. But notice, what do I do with this u right here? What's that u? Well, let's see. According to my diagram and my work here, u is the first input to the g function. Oh my gosh. First input to the g function. That means it's the first output from the f function. And that means it's x squared plus y squared. So, yeah, you got to plug stuff in at the end. But anyway. Okay, last thing we're going to do today, I just want to make sure everyone's clear that you can't overinterpret too much from this diagrams business. I am a big believer in whenever you have a composition of functions, such as here, yes, you should generate, in fact, here's a better example. If you have a composition of functions, yes, you should generate your diagram that corresponds to it. What you can't do is work that backwards. You can't say, okay, any diagram I can possibly dream up and draw must correspond to a composition of functions. No, it's not. It is not. So, notice there's some key things about what I've drawn here. Here is a function. I have a completely independent set of input variables. Different names, no confusion between what the inputs, what the outputs are. Right? And then notice that what comes out of this function is exactly what goes in to the next function, which itself is also very clearly, distinct names for the inputs and the output variables. These input variables are independent of each other. Neither one's a function of the other or anything weird like that. Okay, so that is a necessity if you're going to talk about a diagram as representing a composition of functions. And so, for example, this diagram here, yeah, sure, I'm composing functions because check it out. Here's a function, perfectly well-defined and independent input variables. Its outputs are exactly the inputs to the next function. No problem. Everybody see what I'm saying? If you try to do that with this diagram, it doesn't work. So this little diagram here is not, as written here, a composition of well-defined multivariable functions. It's not. And all of our rules that we wrote down for the chain rule, they were about compositions of well-defined multivariable functions. So we do not have a chain rule for this scenario. And you can't overinterpret and be like, oh, well, I can just kind of keep track of paths and, various things like that. You're going to get into trouble if you try to, venture out onto your own and make up, new points of view, it's precarious. So, for example, let me try to identify functions that we sort of, in some sense, are kind of composing here. The y's are functions of the x's. That's cool. That's not a problem. But what are these z's functions of? And in particular, let's just look at z1. What is z1 a function of? I can't just say that z1 is a function of just y1 and y2 because it isn't. Look at this. It's got an x1 in it. So then I could say, okay, fine. So I will interpret z1 as being a function of x1 and y1 and y2. But now, the outputs from the green function are just not the same as the inputs to the orange function. And worse, the inputs to the orange function are not independent of each other. y1 is a function of x1. Right? What would it even mean, for example, if I were to say, let's talk about the partial of z1 with respect to x1. So, okay, there's z1, there's x1, and I'm taking a partial derivative, so I guess I have to hold y1 and y2 constant. Wait a minute. You can't. If x1 is changing, y1 and y2 are going to change. You can't hold them constant and change x1 at the same time. Just so the point is catastrophe, right? This is not one of these scenarios over here that we're prepared for. Okay, now good news, there's an easy fix in this case, and the easy fix I will point out in this example down here. Notice y1 and colors. Y1 and y2 are functions of x1 and x2. Just like in this example. And let's see here. Go away. Oh my, that's ridiculous. Z1 is a function of, it seems, x1, y1, and y2. And Z2 is a function of just y1 and y2. So this diagram, whatever it represents, is actually, what would come up with these equations. So here's the easy fix. I'm going to come back up here to the picture for a second. In some sense, I'm going to insert a new variable there so that I can view that as a function and that as a function. That's all you got to do is just insert a new variable as needed. And in this case, that new variable is x1, which is really just a placeholder. X1 star is just a placeholder for x1. The value of x1 star is going to be, it's really easy, really boring function. It's just x1. And having done that, no problem. If I want to know the partial of z1 with respect to x1, I want to know this partial derivative, fine, no worries. First path, second path, and third path. Nothing. Oh my gosh, my computer is flipping out. Oh my gosh, it's so weird. Third term. Yeah, I got the message. Okay. 3 terms, and altogether, this is how I compute that partial. No problem. Everything makes sense. Everything's unambiguous. This value, this thing, let's see, where did it go? This thing right here, partial of z1 with respect to x1 star. Oh yeah, that just means this thing right there. Okay. Clear distinction between that and partial of z1 with respect to x1. Right? Because x1 and x1 star are not the same thing, and I can explicitly see the difference between x1 and x1 star right there. Okay, all right, we better quit. My computer's going to start yelling at me. All right, see y'all later. Sorry to go over, and we'll pick up here next time.